Hello, ladies and gentlemen. This is Mr. Kim, who teaches basically all the sciences from Westlock, in Westlock, St. Mary's School. Let's get this started. Today, we're going to talk about conservation of momentum. This video will probably divide it into two pieces. One for lesson and a little bit of a demonstration involved using FET website simulation of collision lab. Followed by, when it comes to second video, it will be about class example solving time. So, please look at those two videos. For people who's encountering this video for the first and who is not from Alberta, I'd like to inform that this entire videos that I'm making follows Physics 30 curriculum made by Alberta Education. So, let's get this started. Hopefully you guys have experience of playing billiard ball games, like 8-ball game, those kind of thing. It is really fun. And the reason is because this is the one where we will see direct evidence of conservation of momentum. As you may see, the game start with the white ball that is collide, have a direct contact by a player. And after that, as you may see, these rest of the ball, they were originally stationary, now are going everywhere. For example, this red one goes diagonally northeast way. When it comes to the striped one, that is also red, goes east-south. When it comes to this yellow, that has direct contact, are going west and south. So, what is this gong show? What's happening in here? And why they're moving such a diagonal way to each other? So we're going to look at basically how these phenomena is happening. And in real life, hopefully it doesn't happen to you, ladies and gentlemen, who's especially teenagers and not scared about speed situation. Look at the red car on the right picture. Probably in this case, you may have an idea. You can deduce some idea from this picture. Red car probably travel towards east or right. When it comes to blue car, it probably travel west or left. And what happened afterward? They had collision. In this picture, both of these cars are basically not moving. So some may wonder, Mr. Kim, what is happening in here? One on the left side, they're moving. One on the right side, they're not moving. What is going on in this situation? Well, that's the point of the lesson today. We're going to look at conservation of momentum in two different situations where everything basically cancel out, which is a picture on the right side. And when it comes to left side, conservation of momentum is happening. However, some of the objects move inside of the system. Technically, what you see on the left side is 2-dimension. So probably lesson 3, we're going to deal with that a little bit more. There you go. Today's lesson involves mainly what you see on the right side. It will be purely about 1 dimension, which means either we're talking about left and right, west, east, those kind of situation, or up, down, north, south situation. And know the fact that when I say up, down, it's like top-down view situation. We're not talking about like throwing ball projectile situation. So let's get this started. Before we getting into actual lesson portion, it is important to think about 3 different type of system. Now, people who had my chemistry 30 class or 20 class already aware that in the world we learn about 3 different systems. And generally, I like to give it as a 3 beaker or 3 cup or glass, whatever you can think of, that has coffee, coffee, coffee. The one on the open situation, this is the end. I don't have any modification in there. One on the middle, I have some kind of lid on it. And one on the left side, I have lid on it. But at the same time, I put that inside of the insulator box or insulator container. So, what's happening in this 3 situation? Well, what you see on the first side, which is an open situation, you can actually freely move everything. So free. People like freedom. Yes, but we're not talking about freedom in this real democratic situation. We're talking about freedom in the chemistry system in here as an analogy. Since it's free, both of the matter can go in and out. That means in this case, coffee and water that dissolve, some of those sugar and so on, those can go in and out, evaporate, or what's outside can come inside, and so is energy. You can have cold coffee if you let it sit overnight, or you can have hot coffee if you put it inside of the microwave, something like that. If you see on the closed situation, you may see that since I have lid on it, you don't actually, or you cannot make the matter go in and out. Probably it will be the same volume as time goes. However, you can actually still make temperature change according to that system. So what that means is if I put it inside of the freezer, well, it's gonna cool down really rapidly. And I'm assuming that I'm not talking about freezing situation in here. It's just temperature change. When it comes to isolated system, this is what I want to focus. This is our key portion in here. Isolated system, we are not making any of the energy movement or mass movement. Now, this is a chemistry analogy. But what does that mean in terms of physics? Well, here's what happened. Please make sure you ready your highlighter. Momentum is conserved collision and explosion only if the system is isolated. The reason being is, can you highlight this? In entire system, there is no net external force that is acting upon. So what that means is, in my fancy way of dumbing down this statement, these two together is, whatever happened inside stays inside. We do not have any of the interference from outside. We do not affect outside just because of what's going on inside of the system. So, before I draw some situation, I want you to go to, if you are electronically accessible, FAT Colorado website. Now, if you have hard time copying this URL, my suggestion is go to Google, put FAT, and when it comes to search screen over there, once you log in, you don't have to log in. Once you go inside of the FAT, you can put collision lab. Then you will see a situation like this. So I went to the advanced setting. I have two of the identical mass. So as you can see, it is a 1 kilogram mass below for the red, 1 kilogram for the green. Now, I differentiated the momentum vector in here. Technically, number one goes east a little bit fast, a little bit more, aka faster in this vector. And number two, towards west, a little bit slower. So let's see what happened. They're gonna have, boom, collision is happening between them. And what happened followed by is, they're gonna travel into different way. Okay, right now it's going 2D because it's really hard to make it into one dimension in here. So let's see one more time. As you can see, boom. After the collision, you see there's a change of direction occur. Now, that's one of the example I like to point it out. If you go to this example in here, collision, we're looking at a system where if two of an object collide, so object A, object B, if they collide, we're going to have a conservation of momentum situation occur. Except, obviously depends on mass and velocity, technically direction too, but we're talking about one dimension, so it will be kind of limited direction, mass, velocity, direction. We're going to look at all these threes. And depends on situation. If it's complete identical, probably it's going to be look like that. If it's not identical, then we're going to see some situation where it's going to go apart. Now, what about explosion situation? Well, explosion situation is, imagine you have originally one grenade. Grenade is a good example, not a good example to use for any of a high school environment situation or any type of education situation, but physics in the name of science, I'm going to use grenade. Grenade, the way it works is it's generally have no motion. However, after explosion, it's going to break it down into several different pieces, and then it's going to travel into different direction. Now, the funny thing about explosion is, since it's originally 0 to start with, you're going to have net 0 momentum even at the end, even after final situation. How that happened? Well, the drawing that I have in here is a little bit two-dimensional situation. If you look at somehow odd way of designing of having a grenade, one that goes west, one that goes east, you may see a little better picture. It's like a tug of war, and y's become net 0. So in next video, let's talk about how we can solve example related to this.